Have you ever really stopped to think about what happens when you click play on a video? I mean, in a split second, data just zips from a server that could be thousands of miles away straight to your screen. It feels like straight-up magic, right? But it's all made possible by this incredible, mostly invisible physical network. Today, we're going to pull back that curtain and look at the actual roads our data travels on.
All right, here's the game plan. First, we've got to learn the language of the network, the basic rules of the road for data. Then, we'll explore the three main pathways it takes. You've got your classic copper wire, the mind-bendingly fast fiber optic cable, and of course, the invisible signals that are flying through the air all around us right now.
So, before we can even talk about the cables themselves, we need to get a handle on a few key ideas that define how data actually moves. Think of these as the fundamental rules of the road in our data universe.
First up is bandwidth. The best way to picture bandwidth is to imagine a giant highway. Bandwidth is simply the number of lanes on that highway. It's the total potential capacity, the absolute maximum amount of traffic that road was designed to handle at any given moment.
Okay, so if bandwidth is the number of lanes, then throughput is the actual number of cars that successfully make it from one end of the highway to the other. Throughput takes into account all the real-world stuff, like traffic jams, accidents, and slowdowns. It's what you actually get, not just what's possible.
And this is where it gets really interesting. Your internet provider, they sell you on bandwidth, that big, flashy number. But what you actually experience every day, what makes your stream buffer or your game lag, that's throughput. This gap is exactly why your 1 gigabit plan might still slow down during prime time. The highway's got plenty of lanes, but there's just too much traffic right now.
So why is throughput almost always lower than bandwidth? Well, it's because the signal's journey is kind of treacherous. Data doesn't travel in a perfect little bubble. It has to fight against a bunch of common problems that can weaken it or even scramble it completely. The first enemy is something called attenuation. You know how a runner gets tired during a marathon? It's the same idea. An electrical or light signal just naturally loses its strength the farther it has to travel. Eventually, it just gets too weak to be understood on the other end.
Then you've got noise. This is literally any kind of unwanted interference that gets mixed in with your data signal. Think of it like static on an old AM radio. It could be coming from nearby power lines, your microwave oven, you name it, and it can seriously garble the message.
And finally, there's crosstalk. This is literally when wires get their signals crossed. The signal from one wire leaks over and messes with the signal on the wire right next to it. This is a huge problem in tightly bundled cables, especially if they're not terminated correctly. It can cause what's called a transmit/receive error, which basically means both ends are trying to talk at the same time. Okay, so let's look at how our first physical medium deals with all these issues. We're talking about the unsung hero of local networking for decades, the twisted pair copper cable. And this stuff is a real workhorse. It doesn't just carry data, it can even carry power, using a technology called Power over Ethernet, or PoE, to run things like security cameras and office phones.
And this chart really shows you just how far copper has come. These cables are rated in categories. You see them as cat numbers. The higher the number, the faster it can go. You can see here that newer standards like Cat 7 can theoretically hit 100 gigabits per second, which is insane. And then there's Cat 8. It's super shielded and built specifically for the demanding environment of data centers, cranking out a steady 40 gigabits per second.
But here's the thing, and this is super important. You can have the best, fastest cable in the world, but the way the individual wires inside are connected at the ends, what we call the termination, is just as critical, maybe even more so. If you get that part wrong, your fancy cable's basically useless.
So, there are two standard recipes for wiring the ends of an Ethernet cable, T568A and T568B. B is the one you'll see most often, but the golden rule, the one thing you absolutely have to remember, is to be consistent. Pick a standard and use it on both ends of the cable. If you mix them up, you're telling one end to send data down a wire that the other end is also trying to send on. It's like two people trying to talk at the same time on a walkie-talkie. Nothing gets through.
But as great as copper is, sometimes you just need more. More speed, more distance, and for that, we have to call in the undisputed champion of high-bandwidth, long-distance communication, fiber optics.
Now this is a completely different ballgame. We are no longer sending electrical voltage down a copper wire. Instead, we are sending tiny flashes of light, literal ones and zeros, down a strand of ultra-pure glass that's often no thicker than a single human hair. It's wild stuff.
And fiber comes in two main flavors. First, you've got multimode.
Think of it like a wide pipe where light from a simple LED can kind of bounce around inside. It's great and less expensive for shorter runs, like inside a building or a data center. But then you have single mode. This is like a perfectly straight, super narrow tunnel designed for a high-powered laser. The light travels in a direct path, allowing it to go for hundreds of kilometers without needing a boost. This is the tech that powers the backbone of the internet, crossing oceans and continents. Of course, you can't just plug a strand of glass into your router. You need a special little module called a transceiver to convert those light pulses back into electrical signals. And as you can see here, these things have evolved like crazy. They started out giving us awesome gigabit speeds, and now we have quad versions that are basically 4 transceivers crammed into one tiny package, letting us hit the massive speeds that make today's internet possible.
Okay, we've covered copper, we've covered fiber, so what happens when we cut the cord entirely? Well, that brings us to our final medium, the world of wireless, where our data literally takes flight.
Your Wi-Fi, your phone's cell service, your Bluetooth headphones, it all works by sending signals through the air as electromagnetic waves. This whole range of frequencies is called the wireless spectrum. Here in the US, an agency called the FCC acts like an air traffic controller, making sure your phone call doesn't accidentally interfere with a TV broadcast.
And the way we control those invisible waves all comes down to the shape of the antenna. A directional antenna is like a spotlight. It focuses all its energy into a tight beam, which is perfect for a long-distance link between 2 buildings. An omnidirectional antenna, on the other hand, is like a bare light bulb. It radiates the signal out in all directions, creating that bubble of connectivity we all know from our home Wi-Fi routers. So, as we've seen, there's no single best way for data to get from point A to point B. It's always a trade-off. Copper is the affordable, reliable choice for your local office network, but it's limited by distance. Fiber gives you breathtaking speed and range, but it's more expensive and tricky to install. And wireless offers us incredible freedom and mobility, but signal quality can be a challenge, and it comes with its own set of security concerns.
Which really brings us to a final thought. It's kind of amazing when you step back and look at it. Copper gave us basic connection. Fiber gave us incredible speed. Wireless gave us freedom. As our appetite for data just continues to grow exponentially, it really begs the question, what comes next? What new medium will we invent to carry our future?